Okay, we're going to talk about chapter 2, divided into two sections. It's our chemistry chapter. And we talk about the states of matter. Solid, it has a defined shape and volume. Liquid, dual volume. You pour your water out, it goes away. Spreads out. Gas is changeable shape and volume, and the gas will fill its container, so it spreads out. Now, this plasma is not mentioned in your book. We're not talking about blood plasma. We're talking about the state of matter, ionized matter, equal number of positively charged and negatively charged ions. And the reason I put it in is because 99% of matter in the observable universe is in the plasma state. Therefore, it seemed as if it were worth mentioning. The sun is where you see this in stars and such. Okay, matter cannot be created nor destroyed in a chemical reaction. It can be converted into energy in a nuclear reaction, but in a simple chemical reaction, it cannot be created nor destroyed. Okay, energy is the capacity to put work or matter into motion, to do work or put matter into motion. Kinetic energy is energy of action, such as moving along. Stored energy is potential energy, such as if you lift something, you climb a ladder, you have potential energy. If you fall off the ladder, gravity has pulled you back down because you stored potential energy in your climb. Okay, types of energy. Chemical energy, and this is mostly what we talk about in this class. Energy that's stored in bonds of chemical substances. Electrical energy results from the movement of charged particles. Mechanical energy is involved in directly moving matter. And then electromagnetic energy. This is like from the sun, visible light, ultraviolet light, X-rays. They exhibit wave-like properties, but they also act very much like a particle, such as light will bend towards gravity or bend when it changes from going through air through water. So it does exhibit properties of both matter and pure energy. Energy is neither created nor destroyed. What there is here. It may be converted from one form to another, and that conversion is usually inefficient because a lot of it's going to be lost as heat. Now, elements are the basic components of matter, and they cannot be broken down unless you use a nuclear explosion. Each has a unique properties, such as physical properties and chemical properties. And they're the building blocks for each element, and they have a simple two-letter chemical shorthand, basically. Oxygen, carbon, hydrogen, and nitrogen make up about 96% of the body mass. 3.9% of the body mass is made up of these other chemicals. Very small part is made up of chromium, manganese, and zinc. Now, an atom its structure is determined by the numbers of subatomic particles. And inside that atom, you have neutrons and protons. Neutrons have no charge, though they do have mass, one atomic mass unit. Protons have a positive charge, they have same mass, one atomic mass unit. Only the protons have anything to do with how a chemical reacts as far as a chemical reaction. The same number of protons, regardless if you have extra neutrons, they're going to chemically combine just exactly like any other thing. Basically, the proton number is what makes a chemical be what it is. Electrons are in orbit around the nucleus, and we have two patterns we look at. They're not exactly right. For one thing, the electrons are shown way too close to the particles inside the nucleus here. The electrons would be way further out. Okay, the planetary model just shows the electrons politely going around like moons around a planet, whereas the orbital model show a cloud of electrons. These two electrons are zinging and zanging in every which direction until it just looks like a cloud. And it's impossible to tell both where the electron is and at what time it's there. So they move real fast. Now, elements, atoms of different elements can have different numbers of subatomic particles. I do have different numbers. Hydrogen, you have 1 proton. Helium, 2 protons. Lithium, 3 protons. The atomic number is the number of protons, and it defines by the very makeup of the nature of the whole chemical idea. The number of protons defines how an atom will react with another atom. The mass number is protons and neutrons added together. The atomic weight is the average mass numbers of all isotopes. An isotope is the same atom, but it may have a different number of neutrons. Okay, here we have hydrogen. This is regular old hydrogen, 1 proton, 1 electron. This is deuterium, 1 proton, 1 electron. They act chemically exactly the same. Tritium has 2 neutrons. Now the problem with tritium is it has 2 extra neutrons and it's unstable. So when you have a nuclear reactor meltdown like did near Tokyo several years back, some water spilled out and this tritium actually became water. You cannot filter it out, but it's radioactive. These neutrons are going to be given off, and therefore water that came out of that plant is radioactive. Okay, radioisotopes spontaneously decay. That means they get rid of those extra neutrons, and they act chemically exactly the same as any isotope, and you can detect these with scanners such as a Geiger counter. Now, people want to know about carbon dating. Well, this guy was dug up, I think it might be a female, woolly mammoth, I think, was dug up out of some ice somewhere where I don't know, very, very far north anyway. Maybe Siberia, I'm thinking. But they decided how long that animal had been dead. I don't remember, 5,000 or 6,000 years old. And the idea behind carbon dating is we know in the atmosphere the ratio of carbon-12 to carbon-14. Now the carbon that's in the grass that this guy ate came from the atmosphere, because what plants do is they take atmospheric carbon dioxide and using the energy of the sun, they assemble them into chains such as glucose, complex carbohydrates. And then as the animal eats them, he digests them and incorporates them into his own body tissues. Now it's reasonable to assume that once you're dead, you quit eating. So he gets no new carbon particles. So therefore, the age of this guy can be determined by comparing the ratio of carbon-12 to carbon-14 in the atmosphere to the ratio in him. He will have less carbon-14 than the atmosphere does because it degrades. It's somewhere around 5,000 years change is the half-life of carbon-14. And so that's how they determine how old he is. Okay, radioisotopes are used for treating things like cancer. You can take little pellets and put them in a cancer, little pellets that are radioactive, and they'll kill cancer cells without killing other cells. Now, a bad thing, radon, which comes from uranium decay, causes lung cancer. Now, if you live in a nice, new, well-sealed house that happens to be built on uranium mine, that uranium is going to decay into radon, and radon is going to accumulate in your house because you don't have a lot of ventilation, because that makes your house efficient energy-wise, and you're much more prone to lung cancer. Okay, molecules and compounds. The difference, molecule is just two or more atoms bound together. And you see here, H2 is a molecule, but it's not a compound. Compound, you have to have different kinds of atoms. Okay, matter exists often as mixtures, physically mixed components. And we divide them into three types: solutions, colloids, suspensions. A solution is a homogeneous mixture. Seawater, atmospheric air, Kool-Aid, salt water. Okay, the solvent is going to be the amount present in the greatest amount, usually a liquid. The solute are the particles. Okay, we can talk about concentration of solutions in percent, parts per 100 parts. So if you had, say, a liter of normal saline, and you wanted that to have 5% of chemical X that you had in a vial, you could pull out, say, 5%, you could pull out 50 mLs out of your liter and then put 50 mL of your chemical X in, and then you'd have a 5% solution. Okay, milligrams per deciliter is used simply because it comes out to be real convenient for things like blood glucose. Nobody wants to read blood glucose, and instead of it being 78, it would be 7,850 or something. Nobody wants to read them in those weird numbers. So this is used for most of our blood tests. And then molarity is moles per liter. A mole is the atomic weight of an element, basically in grams. A mole also contains 6.02 times 10 to the 23rd particles, and that's Avogadro's number. It's like a dozen. A dozen eggs has 12 eggs. A mole has a whole bunch more. This should be a time signal, but something went wrong with the translation here. A mole is 6.02 times 10 to the 23rd particles. And assuming I counted out the zeros right, this is the number. So it's like a dozen is 12 eggs. A mole is a whole bunch, this many particles, eggs, atoms, whatever you want to count. Now, a colloid is a heterogeneous solution, translucent. Cytosol, which is inside the cells, jello, large particles are in there that reflect light. They do not settle out. Now, suspensions are heterogeneous mixtures. Now, both are heterogeneous, so they got different stuff, but they do settle out. Muddy water, you shake muddy water up, and you let it settle, you'll see clear water on the top and mud on the bottom. And the same with blood. Okay, we have a solution here. Here's sodas. If you can imagine, someone actually makes baking soda. Baking soda, bacon soda. It's tragic. Okay, a colloid example would be jello. And suspension, an example would be blood. If you, this is an example that has no doubt had an anticoagulant added. You let that settle, red blood cells go to the bottom, the white blood cells and platelets go here, and the plasma stays on top. Mixtures, as opposed to a compound, you can physically separate the mixtures, whether they're heterogeneous or homogeneous. This salad is a heterogeneous mixture. You can just pick out the lettuce, pick out the carrots, and then you have a stack of lettuce over here and a stack of carrots over here. Now, even a solution that's homogeneous, like salt water, you can separate salt and water. You just boil the water, and especially you capture it into a tubing and then condense it down and distill it out. You'll have water in one container and salt in the other, so they can be physically separated. Now, compounds, the only way to break down a compound is by breaking bonds. So they're going to have to be homogeneous. That means they're the same because it has a specific chemical structure. And if you did not know, every little point here represents a carbon when you're looking at organic compounds. These are all carbons here, each one of these little arrows, these little corners. Okay, chemical bonds. Now, the electrons are going to occupy energy levels, and there's a rule called the Octet Rule. It's kind of a bad name because the first energy level has 2 electrons in it. That's what it will hold, and it can hold and must hold. The next ones hold 8. We call the outermost shell the valence shell. So first holds 2, the next one holds 8, 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 and so forth. And they must feel just as surely as if you jump off the top of that ladder we talked about earlier, you will fall. Well, they will fill their shells. It just does happen. If I find my right place here. Okay, helium is an inert chemical, as is neon, because helium has 2 protons and therefore 2 electrons. Its outer shell or valence shell is full. Same thing with neon. It has 2 electrons in the middle because we have 10 protons. So 2 plus 8 electrons. So both shells are full, so it's inert. It cannot react with anything. Now, chemically reactive things. Hydrogen has got 1 electron in its outer shell. It's completely unstable. It cannot exist in that matter. So it's going to have to either give away this electron or share this electron. Carbon has got 4 in its outer shell. It needs 8. So it has 4 places in which it can bond with other things. Sodium has got 1 electron in its valence shell. Again, that's extremely unstable. It must either bind with something or give away that outer electron. Oxygen, again, is reactive because it has 6 electrons in its outer shell. It needs 2 more. Okay, outer shell is going to fill up, not because it wants to, but it must. It's the same law, it's a stronger law than the law of gravity. You're going to fall if you fall. So sodium has 1 in its outer shell, 1 electron. Chlorine has 7 electrons in its outer shell. So what they do is they get together and solve their problem by the sodium donating an electron to the chloride. This makes the sodium be positively charged and the chloride be negatively charged. Now they are bound and they must bind together because that's just the nature of them. They must do so. Okay, types of bonds: ionic, covalent, and hydrogen. Okay, ionic bonds are formed by the transfer of electrons between atoms, and you end up with a negatively charged atom that has gained an electron. So if you gain 1 or more electrons, you've got too many and they're negative, so you're going to be negatively charged. Cations are positively charged, but lost 1 or more electron. And opposites attract, and so the anion and the cation will be attracted to each other, and therefore you have an ionic bond. So here we have our sodium and our chloride, and the sodium is giving up its electron, and now you've got a positive sodium and a negative chloride. Now, because of the fact that they're attracted to each other, when they come out of solution, they're going to form crystals because this chlorides are green here in this case. Chloride is attracted to the sodium, which is attracted to the chloride because we have negative, positive, negative, positive. And just because this one may have originally, these two may have originally been bound together, these two may have been originally bound together, this chloride is still attracted to this, and so on and so forth. So they are, each is attracted, negatives and positives attract each other. Now we also have covalent bonds. They actually share their valence shell, and they share 2 or more electrons in their valence shell. And this is an example here. Carbon needs 4 places to an atom. You have 4 hydrogens, they get together, they bind up, and you get methane. Okay, oxygen, it has 2 places it needs to bind. So 2 get together, you have O2 and a double bond in between. Okay, nitrogen does the same thing, but it shares actually 3 electrons. So we have a triple bond. Okay, this is a question. Is sharing always fair? Is it possible if these 2 individuals are sharing a pizza that they may not share equally? And we discussed in class, yes, it is quite probable that this individual is going to acquire more pizza than this individual because he's bigger, he has a greater affinity, a greater pull, and a greater ability to pull more pizza towards him. Well, covalent bonds may be sharing their pizza, sharing their electrons equally, or they may not. So if they share equally, we have a non-polar bond, such as carbon dioxide. The carbon and the oxygen, they get together and they share equally. They're non-polar. Unequal sharing, you end up with basically, in this case, you have your hydrogen. Let's go to the next page. Your oxygen takes more time. It has a stronger affinity for the electrons. So this side is negative, and these sides end up being relatively positive. And that is why hydrogen bonds, which we will discuss in detail on the next little quick show here. So the 3 types of chemical bonds: ionic bonds, you have transfer of electrons. Polar covalent, you share but you do not share equally. You have polarity. One side's negative, one side's positive. Non-polar covalent, you have equal sharing. It's balanced sharing. Now, one thing I will mention here is that polar stuff and non-polar stuff don't mix. Water is polar, oil is non-polar, and you already know oil and water don't mix. And the reason is because of the differences in their polarity.